Well, hello. Thanks for coming back to my YouTube channel. My name is Rich Roberts, Dr. Rich Roberts, whatever. If you want to see my credentials, you can go to the description underneath this video. And after I give a short description of the video, I have my credentials down there. But I'm a medical doctor, in brief, a doctor of biophysics, and I was the president and CEO of a pharmaceutical company for 24 years. Now, I'm here to speak with you today about giving you an overview of all of science, and then in particular we'll go into quantum mechanics, special relativity, general relativity, understand dark matter, elementary particle physics, and then we're going to get into UFOs, which is unidentified flying objects. The military calls it UAPs, unidentified aerial phenomena. Now, I just want you to know that the idea of like UFOs has always been, for the most part, people felt the purview of really nutty people who just made up stuff, crazies. And the truth is, there are certainly a lot of people that have been in that for a long time. But the entire UFO discussion has now switched or changed, and I'll give you the details later. But since the United States military, the Pentagon, has acknowledged that several videos that leak are in fact authentic, and the characteristics that we see in those videos and what you hear, we're going to hear from two previous presidents, President George W. Bush and President Obama, how they can't talk anything about it, and some other information. It looks like there really is extraterrestrial life. If anyone is going to think clearly about it with an open mind and look at the facts, it really does look that way, but we're going to get there in a little while. Lastly, as I've told you before, I don't make any money on my YouTube videos. I don't commercialize it. There's no commercials. There's no Patreon or any way to donate money to me. There's no merchandise to buy. The only way that I can really get a payment from you is for you to leave a comment below. Tell me if you like the video or not. And also, please subscribe. Please subscribe. I try to do these videos, and we try to do them once a week. It's a lot of work. We're going to try to do once a week. I'm going to go across a wide variety of topics and hopefully be able to provide you some really good information. So that's it. Let's get moving forward. The first thing you need to know in terms of understanding in a certain way all of science is observable versus theoretical science. And let me explain this to you. You can look at any system, I don't care what the system is, and you can break it down by various aspects to it. So for example, let's say, let's look at all types of fruit. We can break down fruit by mature fruit that's over 1 pound or under 1 pound. Which fruits are they? You could break it down by fruits that grow on trees versus ones that grow on vines. And you can go down, you take fruits that are red versus fruits that are green on the outside. You can do it in yellow and whatever you want to do. You can make all these different ways of breaking things down. You do that with any system. In medicine, we might look at the nervous system and say, well, the central nervous system versus the peripheral nervous system. The central nervous system is the brain and the spinal cord, and the peripheral nervous system is all the nerves that go out from there that make you feel or do anything in your body. Or we might break down the nervous system in terms of sympathetic versus parasympathetic. The sympathetic nervous system is your fight or flight. It's when, a tiger jumps out at you from behind some bushes, and then you release adrenaline, and which is epinephrine, and also norepinephrine and cortisol. Blood to your kidneys is shut off. Blood to your skin is shut off to concentrate the flow of blood to your muscles, where you're going to need to either to run or to fight. And you can compare that nervous system to the parasympathetic nervous system, which is we call the vegetative nervous system. When you're sleeping, when you're resting, then blood is sent mostly to your intestines to digest food, and your kidneys and your skin, and it's run generally by the hormone acetylcholine and not epinephrine or norepinephrine. So you can break down nervous systems physically, anatomically, chemically, fine. So let's break down all of science. You can look at all of science, you can break all of science down to what is observable versus what is theoretical. In other words, and by the way, and the only certain science is that which is observable, that you can see with your eyes, and you can actually test by seeing it yourself. When you get to theoretical, as you will find when we go further into this, you don't really know if your theories are correct or not. And every scientific theory, for example in physics, has been overturned at a later date by a new theory that not only includes what the other one claimed to have been able to follow, but also it predicts and explains new things that are happening. What is that? Is that a knock at the door? I'm sorry, I gotta go check this. Okay, so let's see who's at the door. Wonder who came to visit. So with medicine, for example, we take 1,000 patients with pneumonia, and of course you control for how you're diagnosing the pneumonia by x-rays, by pulmonary function tests where people inhale. I don't want to go into all that, but pulmonary function tests to see how well the lungs are working. And then you give, let's say, 500 of them an antibiotic and 500 of them don't get the antibiotic. And then you find, and by the way, but all of them get the same looking pill. And even the doctors giving them the drug don't know what the drug, whether it has the drug or whether it's just a sugar pill. And then you find the 500 that got antibiotics, 99% live. And the 500 that did not get antibiotics, 99% died. Then you do statistical analyses to say, if I had a group of 1,000 patients, and it just by sheer luck, we happen to come out with a result of 99% living with the antibiotic, 99% dying without the antibiotic. We then do statistical tests, and it comes out, it's called the p-test, to determine what the likelihood is that this is a real result versus that it actually might just be an artifact, it might be a random result. So of course, if you do such a study 1,000,000 times, some of them would come out with very different results just by the random luck or lack of luck of the draw. So medicine in that sense, when they do double-blind placebo-controlled studies, is really true because we're looking at it, we're observing it directly, and then we're doing statistical tests and we're saying what's the degree of reliability that it is actually true or not true. And that's how medicine is done. That's something you can observe. But when you get into things that we can't observe, then you get into theoretical science. And I'll give you examples. For example, you all know what atoms are. Do you know that we've never seen an atom? Do you know that no one has ever seen an atom? Do you know that you cannot see an atom? It's called the Heisenberg uncertainty principle. I don't want to go into the details of it, but it has to do with an uncertainty in the position times an uncertainty in the movement. The velocity is always greater than a certain number. So if you have an atom there, and you try to see it with light, and a particle of light hits it and bounces off to your eye, well then you need, if you wanted to see me, you'd have to have particle light bouncing off here, everywhere at the same time. But an atom, particle light hits it and bounces off to see your eye, because the atom's so small, it actually moves a little. Next time a particle light would hit and bounce off, you don't know what part of the atom it hit. So it's called the Heisenberg uncertainty principle. So when you look into theoretical physics, scientists try to come up with mathematical formulas, mathematical equations, and don't be mistaken. We're going to speak qualitatively in this video. We're going to speak about the qualities of what these scientific theories mean, but we're not going into the hard mathematics. Without the hard mathematics, nothing matters. People can speculate, have an idea. I think that particles are made of energy and blah blah blah. But if you can't come up with the mathematical equations that show what's going on, and especially as you see in the case of Albert Einstein, predicting things that weren't shown experimentally until years later, then you're really qualified as a leader in science. Yeah, so it's interesting to note that theoretical science is not just physics that's dealing with particles that are so small that no one could ever see them. Even look at an area like anthropology. A lot of these things are stories that are made up. It's just a hard fact. They'll find a human bone from a leg, and they'll see the indentations in that bone are very deep. So then they'll say, so that means that they had a very strong muscle on that leg bone, which means that leg bone was was abnormally strong, so they were pushing a plow, and that means they had an agricultural society. And if it was an agricultural society, then they had to have other products they were bartering with, but they probably had to have money. And they started going this whole story from some deep scratches in a bone. And the fact is, they don't really know that any of it is true. They just made it up. And you'll find, if you look at science, a lot of that science sort of gets away from people, and people like self-reinforce, and they'll make up stories and upon stories, and they'll self-reinforce. And if you actually go back to, do you really know if that's true? The answer is they don't really know if it's true. So what we do is, in theoretical science, if the theory is able to, the more the theory is able to explain what we've already seen, and the more that it's able to, especially in physics with mathematics, give you calculations that you can use to show how things happen, and also hopefully in the future predict how things will happen in experiments and in the physical sciences, then we get a greater and greater degree of belief in the likelihood that is actually a true theory. But you must know that every scientific theory has always been overturned across time by better theories that both encompass it and explain things that this theory could not explain. So with those qualifications, let's now talk about quantum mechanics. There's a difference between energy versus matter. For example, if I pick up this battery and I put the battery in my hand, you know the battery's there, right? Good. Now, light is traveling as a wave. Oops, I caught it in my hand. Is the light in there? Oh, I can't see it. It got away. As a matter of fact, if you look at a wave going through the water, I had always thought that the wave coming, you see that wave coming this way? I thought it was water coming this way. It's not. The water, if you see a wave coming in from an ocean, the water is staying where it is. It's just getting lifted up and down by an energy wave going through it. But the water isn't actually moving itself. When you see it crash on the ground, that's to do with the wave coming up high and then hitting the shore and then smashing and going backwards. But it isn't actually propelling, as the wave travels, not propelling the matter that is going through up and down, forward. It's just going up and down as the wave goes through it. So there's clearly two forms of matter and energy in the world. There's matter, physical things you can hold, and there's waves that seem to just travel through matter, but they are not matter themselves. So in quantum mechanics is based upon a very interesting experiment. It's called the double slit experiment. Double slit experiment. If you have a pond of water and you throw a pebble in it, you'll see waves, waves go out from that pebble hit, waves go outward in all directions. Now, if I throw two pebbles at opposite sides of the pond at the same time, the waves spread out from where that pebble was, and then they hit each other, the waves. And where they hit, that the one wave is up, the other wave is up, you get even a higher wave. But when one wave is up, the other wave is down. It's called the peak and the trough. When they hit each other, you have flat water. It's like there's nothing even happening. So here's an interesting experiment. If I take a wall, I'll take a wall here, okay? And I'm gonna put a slit in it. And now I'm going to close my eyes and just throw baseballs at it. Well, some of the baseballs are going to hit the wall and come back, but some of them are going to get through that slit, make a slit wide enough the baseball gets through it, and they're going to hit a wall in the back where I'm throwing to. I just keep throwing and throwing. Now I'm going to make these balls have carbon on the outside of them. So when they hit the back wall, or they could have paint, they hit the back wall, they make a spot. As you can imagine, if I'm throwing blindly through this slit in this direction, and I throw whatever 1,000 balls, then the center is going to have more dark hits on it where the balls hit, and a little outside will be less, and then less and less and less. More of my balls are going to hit towards the center, off this way, that way a little, and less as you go off, to wide angles. Great. So now if I take the slit, I take a slit and I throw electrons at it. What I do is I have an electrical plate here that's negatively charged, a plate here that's positively charged. And I drop electrons right in front of the negatively charged plate. The electrons are repelled, electrons are negatively charged, they're repelled by the negative plate, and they smash into the positive plate. They're repelled by the negative plate and they smash into the positive plate. I'm going to put a little hole in the positive plate. So some of those electrons, not a hole, I'm going to put a slit. Very, very thin slit. And some of those electrons are going to go through the slit and hit a screen in back of it. And as you can imagine, you'll get just like I did with my baseball throwing. You're going to get in the center, mostly dark with the electrons hitting, and then less and less and less and less. Now, I'm going to do 2 slits, my experiment. I'm going to have two slits that the electrons are trying, or put electrons here, let them fly out. And sometimes they go through one slit, sometimes through another, but the electrons go flying out. And they go through the 2 slits, and when they hit the screen in the back, what happens is amazing. You don't see dark portions where the 2 slits were and lighter. You see lines. And those lines end up being where if there were waves going out of those 2 slits, and those waves were interfering, where the 2 waves are high, you get a dark line. Where one was high and one was low, you get blank. So you say, whoa, when these electrons go through 2 slits, these electrons, which are matter, not waves, they're matter, they are interacting with each other like the 2 pebbles in a pond. They're acting like they're waves interfering with each other, either up or down, or up and down, which is 0. That's amazing. The next result, though, is mind-blowing. Now we do the same experiment with 2 slits, but this time we only let 1 electron shoot at a time. 1 electron at a time. Let one go and put another electron and let that go. So you know they can't be interfering with each other. In other words, the electron will go through one slit or the other slit, but you don't have 2 electrons at the same time with waves somehow, whatever that means, interfering with each other like the pebbles in a pond, making interference patterns. You won't have that. When you send 1 electron at a time and you have 2 slits, you end up on the screen again with stripes, vertical lines, that the electrons are going by an interference, like going by a wave interference pattern, even though there's only 1 electron at a time. So it turns out, through what's something called the Schrodinger equation, we can figure out that there's a mathematical equation that is called the wave function, or the eigenfunction, that goes with every particle in the universe. And that wave function, which is a mathematical formula, changes if the energy of the system changes. In other words, if you have 1 slit versus 2 slits, even though you can say that can't be. The electron is the electron, right? It only experiences 1 slit. It goes through 1 at a time. Nope. The energy structure of the system is affecting whether the electron will act as a particle or act as a wave. And that function, that wave function, is the probability that you will find that electron or whatever particle is in the universe at any place at any time. And when the energy level, for example, electron in an atom, if it jumps to a next energy level, bang, just jumps up, the wave function, the mathematical function that is the probability of where that electron will be found, changes. So you have this particle goes through a mathematical probability function change when it changes energy states. Which, by the way, I'm sorry to inject religion into this, but me as I'm an Orthodox Jew, and I say the dumbest thing you can imagine is a particle. Has no nervous system, has no brain, has no intellect, just a particle of matter. And yet it reacts or interacts or acts by the most complex mathematical equations that only the smartest people in the world can go that far in mathematics to understand. So how does a particle operate according to sophisticated intellect? Think about that. Okay, let's move on to more science. Okay, so now we're going to speak about Einstein's theory of special relativity. All right, what is that? Is that a knock at the door? I'm sorry, I got to go check this. Okay, so let's see who's at the door this time. Oh, it's our special guest. Come on in. Well, thank you for coming on my show. I do have to admit I'm a little bit uncomfortable. I've never interviewed an alien before. So how do I communicate with you? Do you speak? Oh, very nice, very nice. But I don't speak computer language. Can you speak like a human language? Nosh, Kugel, Schnaps, Mizummin, Bizunda. Oh, that sounds like a human language. I'm not sure which one. but I speak American. Do you speak like American? I don't mean English, where they say controversy, where we say controversy, or they say call it a lift, we call it an elevator. Do you speak like American? I've been an alien since I was born, traveling the galaxies, a story forlorn. Lost for a long time, a very long trip, trying to get back to my mother's ship. Traveling at an amazing clip, wow, my ship really could rip. I showed up on Earth, Pentagon studied me. Why won't everyone just let me be? Yes, nuclear reactors interest me. To them I have a propensity. It's not a case of religiosity. I have a big curiosity. I just like the intensity. I am here to do no harm. I come fully unarmed. You should not be alarmed. I'm just here to study your charm. Being here, I would not rather, but I traveled through dark matter. Using a catalytic reactor, I come as a peaceful actor, and I am no attacker. I just got the message to return. My planet called me, no concern. About you I have learned, but going home I do yearn. I will give a very good report. Time to home is very short. Seeing planets is our sport, but my leaving you cannot thwart. Whoa! Did you just see that? Where did it go? Okay, we'll continue on. Now we're going to talk about Einstein's theory of special relativity. If there's a train moving at 5 miles per hour, if I'm on the train, and I'm on the train, I'm moving at 5 miles per hour. That's how you see me, because you're standing on the ground. And I take a ball while I'm on the train, I'm moving at 5 miles per hour, and I throw it at another 5 miles per hour. You're going to see it go 10 miles per hour. The 5 miles per hour that I'm on the train going with, and the 5 miles per hour with which I throw it. So you're going to see it going 10 miles per hour. What Albert Einstein said is, the speed of light never changes. And it's when you get into advanced physics, things become what are called counterintuitive. They kind of don't make sense to our normal reality, but it seems that this is the way the universe acts. So if I'm on the train and I'm going at 8/10 the speed of light, I'm going at 0.8 the speed of light, shoo, right? So you couldn't really do this experiment with a real person, or going on a train, because the speed of light is 396,000 miles per second. So if you think from New Jersey, where I am, to California is about 3,000 miles. The speed of light can go 396,000 miles per second. But if I was traveling on a train going at 0.8 times the speed of light, and I threw a ball at 0.8 times the speed of light, you should see the ball go my 0.8 speed of light plus I threw it 0.8 speed of light. You should see the ball going at 1.6 times the speed of light, 0.8 plus 0.8. But nothing can go faster than the speed of light. So using this contradiction, or this property of the universe, that's how Albert Einstein came up with his theory of special relativity, where he has an equation that shows that as people or particles or whatever go close to the speed of light, time slows down, weights increase, and things will lengthen. So it sounds bizarre, but what happens is, if you look at the equation, for those, I don't want to do hard science, but if anybody wants to look at it, it's called the special relativity radical. It's the square root of 1 minus v squared over c squared. V is the velocity you're going, you square it and put it over the speed of light, and it's 1 minus that, so and there's the square root. So if you're at speeds like anything in our lives, in normal human interaction with the universe, we go so slow, even our fastest jet fighters go so slow that the difference you can't even detect. And that's why, if you've ever heard of Sir Isaac Newton, a brilliant person who developed physics and developed calculus, the whole field of calculus, just so he could do his physics. He has what they're called the Newtonian laws of physics. And whereas he said that this should go 1.6 times the speed of light, that's because he never experienced anything going anywhere near the speed of light. And the slight bit that his theories were off, at our levels of speeds, you just can't even detect. But Einstein showed that it's real. So this has been shown in linear accelerators. I'm going to show you a picture right now of the Stanford University, a Stanford Linear Accelerator. It's a 2-mile long, perfectly straight tube building with a thin tube inside. And what they do is they can drop an electron between two charged plates, one negatively charged here and then one positively charged with a little hole in it. So the electron is shot away from the negative and towards the positive. And the ones that go through that little hole can go very fast. How fast? These are basic physics formulas, because you know how much, how strong the electric field was between these two plates. You know the charge of the electron, and when it goes across that field, you know how much energy was added to it, so you know how fast it's going to go. Now, if you're in a car traveling at 60 miles per hour, and you travel for 1 hour, how far did you go? 60 miles. So when this electron travels now at close to the speed of light, you know in how much time it should be a certain distance down that 2-mile tube. And it turns out it ends up further down the tube. Why? Because as it goes close to the speed of light, time slows down for it. So it's able to travel further in what we think is a certain period of time, because the time it actually slowed down for that electron, and it can reach further. How much further? Einstein's theory of special relativity, square root of 1 minus v squared over c squared, tells you exactly where that electron is going to show up. It's a tremendous discovery and formulation that Albert Einstein worked out. Interestingly, he never got a Nobel Prize for that.